When you say the internet is down, what's actually broken? Your Wi-Fi, a fiber line under the ocean, or just one website refusing to load? We toss around internet and web like they're the same thing, but they're two different layers, and that difference matters. In this episode, we'll trace the Cold War roots of the infrastructure, the invention of the World Wide Web, and the mobile shift that put a full-time network in your pocket. To help us separate the pipes from the pages, I'm joined by our tech historian. Big picture, what's the actual difference?
Think of the internet as the road system. Cables, routers, and the rules that move data from place to place. The web is one popular thing that rides on those roads. Web pages and web apps you reach with a browser, using URLs and HTTP.
So when I send an email or stream a movie, I'm using the roads, but not necessarily the web.
Exactly. Email has its own protocols, and streaming can happen without you ever opening a browser. They're all internet services, but the web is just one of them. It helps to picture it as a stack. The physical connections at the bottom, then addressing and transport, and then the apps up top.
And scale makes the distinction real. By 2025, global estimates put internet use at about 6 billion people. So when something breaks, a lot of life breaks with it. A damaged undersea cable might slow down or isolate whole regions, and a DNS failure can make it feel like the internet is gone, when the wires are fine. You just can't find the addresses.
Right, and that stack has a history. Packet switching ideas show up in the 1960s. Then, networks grow into a global internet. And now, we're building massive cloud platforms on top of it. First, we laid the tracks. Then, we built the trains.
Let's go back to the very beginning. Before we had the web, we had to build the pipes.
To understand the internet, you have to picture computers as expensive islands, like the lonely mainframes you're seeing on screen. In the early 1960s, getting two machines to talk often meant setting up a dedicated circuit between them. It worked, but it was costly, and if that line had trouble, the conversation died.
So it was like a telephone call. You had to open a line and keep it open.
Exactly. Circuit switching. Once you reserve the line, you've reserved it, even for silence. But in the early to mid-1960s, researchers including Paul Barron at Rand and Donald Davies at the UK's National Physical Laboratory pushed a different approach: packet switching.
Packet switching. Is that where the digital envelope analogy comes in?
Yes, and that side-by-side visual makes it click. Instead of one dedicated pipe, you break a message into small, numbered packets. Each packet can take its own route, and the receiver reassembles them. If a path is congested or a link fails, packets can be rerouted without rebuilding the whole connection.
That sounds much more resilient. So, who actually built this first?
ARPA, part of the U.S. Department of Defense, funded ARPANET, and by December 1969, it had 4 initial nodes: UCLA, SRI, UC Santa Barbara, and the University of Utah. Just like that hand-drawn network sketch on screen. But here's the key. The big mainframes didn't do the switching work themselves. Each site got a dedicated mini-computer called an IMP, an interface message processor, built by BBN. It's a direct ancestor of today's routers.
It looks like a giant refrigerator. And this machine handled the traffic so the main computer could just focus on computing?
Right. The IMPs talk to each other over leased telephone lines, initially at about 50 kilobits per second, which was a big deal at the time.
50 kilobits. That's a tiny fraction of a modern connection. So, what was the first thing they said on this new network?
It wasn't profound. On October 29, 1969, UCLA tried to log into the computer at SRI. They started typing login, and you can see the drama in that printout close-up.
Let me guess, the system crashed?
It did. Only the first 2 letters, L and O, made it through, before the remote system crashed. About an hour later, they got it working and completed the login. But ARPANET still had a limitation. It ran on a protocol called NCP, the Network Control Program, which was fine inside one network, but didn't scale to many different networks talking to each other.
Wait, I thought ARPANET was the Internet.
Not yet. It was a network. In the 1970s, there were other packet networks too, over satellite links and over radio. The challenge was getting those separate bubbles to interconnect into an internetwork. That's where TCP/IP comes in. Bob Kahn and Vint Cerf led the design of a protocol suite that could move packets across different kinds of networks. IP for addressing and routing, and TCP for reliable delivery when you need it.
So TCP/IP is the glue. When did we actually switch over?
January 1st, 1983. Often called the ARPANET Flag Day. It was a coordinated cutover from NCP to TCP/IP. If your system didn't make the change, you effectively couldn't communicate with the rest of the network. That switchover is widely treated as a major milestone in the birth of the modern Internet. But for most people, it was still invisible. Green text on black screens, command lines, and terminals. We had the pipes. Next, we needed a window.
If the Internet is the plumbing, the World Wide Web is the first time someone put a faucet in every kitchen. Before 1989, the pipes were there, but you had to be a plumber to get any water out. And that's what you're seeing on screen. The hidden pipes on one side and the friendly window on the other.
That framing really works. Technically, the web is just one application that runs on top of the Internet. It was invented at CERN to solve a very specific problem. Researchers were spread across different computers and systems, and sharing documents was messy.
So it wasn't built for social media or shopping originally?
Not at all. In March 1989, Tim Berners-Lee wrote a proposal called Information Management, a Proposal. Basically, a plan for a distributed information system. And on screen, you're looking at one of the early web proposal drafts from that period. The core idea was simple. Link documents so people could jump from one to another, even across different machines, without a central gatekeeper.
And to make that work, he needed a recipe. I've heard it described as a three-part system. Can we break down the ingredients?
Absolutely. The web is built on three simple agreements. First, the URL, an address, where a thing lives. Second, HTTP, the request and response rules, how a browser asks for a page and how a server sends it back.
And the third one is HTML, right? That's the language that tells the page what it is.
Correct. HTML tells your computer, this is a heading, and this is a link. Berners-Lee also built the first browser editor and the first server to prove the whole stack worked. He ran it on a Next computer at CERN.
And we've got that photo of the first server. Behind the glass, there's that taped-up warning. This machine is a server. Do not power it down. It's a great snapshot of how small this was at the start. If that box went down, the first website went dark.
It really was fragile at first. But the turning point was what happened next. CERN gave the core web software away. On 30 April 1993, CERN released it into the public domain, making it freely available for anyone to use and build on.
That seems like the critical turning point. There was a competitor called Gopher at the time, right?
Yes, Gopher was popular, especially for organized menu-like directories. But in early 1993, the University of Minnesota announced it would start charging licensing fees for commercial use of its Gopher server software. That uncertainty spooked people. Meanwhile, the web was openly available, so developers piled into the path with fewer strings attached.
So the pipes are open, and the recipe is open. But it still looked pretty plain for a while. When did it start feeling like the window we use today?
That changed in 1993 with a browser called Mosaic. Earlier browsers could be pretty text-heavy, and images often felt bolted on. Mosaic made it feel unified, text and pictures together. So the web stopped looking like a lab tool and started looking like media.
And that visual shift helped kick off the boom. By 1994, companies were jumping in. We got Netscape Navigator, and suddenly the browser felt like a product.
Netscape helped turn the web into a commercial platform. They introduced things we now take for granted, like cookies, and early web security with SSL. And by their IPO on 9 August 1995, the web was no longer just a research project. It was a marketplace.
So in 6 years, we went from a March 1989 memo to a 1995 IPO. We had the address, the transport, and the language. Next, the world needed speed, because the faucet had turned on.
Exactly. The dial-up screech was about to be replaced by the hum of broadband. And eventually, for a lot of people, the cables would fade into the background entirely. By the early 2000s, the internet stopped being a place you went and started being the air around you. Wi-Fi did that. Suddenly, the network wasn't a cable in the wall. It was ambient.
I remember that shift. But Wi-Fi just untethered the computer. It didn't change how the internet worked, did it?
Not the protocols, no. But the economics and infrastructure shifted hard in 2006. Amazon launched S3 for storage and EC2 for compute. We call it the cloud, but it was really a new way to rent the guts of the internet.
So instead of buying a server rack, you just rented one.
Exactly. Like switching from buying a generator to plugging into the grid. You could scale up fast without owning the hardware. And then, in 2007, the screen shrank.
The iPhone.
The iPhone, and then Android. The internet moved into our pockets. And when the App Store arrived in 2008, the web stopped being just pages you visited and started being apps you carried.
It feels like that was the moment the internet became a utility.
And it became truly universal. The ITU estimates that in 2025, about 74% of the world, around 6 billion people, used the internet.
And I assume most of that is mobile now.
In subscriptions, yes. The ITU puts 2025 at about 9.2 billion mobile cellular subscriptions worldwide. But that's not the same as 9.2 billion people. Many folks have multiple SIMs, and plenty of those lines belong to devices. And most of the heavy lifting is still done by fixed networks. In 2025, the ITU estimates mobile broadband carried about 1.5 zettabytes of traffic, while fixed broadband carried about 7.3, nearly 5 times more. We walk around with phones, but we run on Wi-Fi, fiber, and data centers.
With that much data moving around, security must be a nightmare.
It's a constant battle, but we did lock down a huge leak: encryption. Let's Encrypt made HTTPS cheap and automatic. And today, on most platforms, Chrome sees roughly 95 to 99% of page loads happening over HTTPS.
So the pipes are more secure, even if the volume is higher.
More secure against casual snooping, yes. But the scale of attacks has grown with the network. 2025 saw record-setting denial-of-service floods, pushing up toward 30 terabits per second. When the internet becomes critical infrastructure, the threats become infrastructure scale too. It's no longer just a research network. It's the nervous system we depend on.
If we boil this whole story down to one idea, it's tracks versus trains. The internet is the track system, the thing that moves packets. The web is one very popular train running on top of it.
Exactly. We didn't just build a network. We built a stack of agreements. You can see it in the layers on screen. Physics first, then addressing and routing with IP. And once that's in place, higher layers can finally assume the network exists and build on it.
Then the apps exploded. Websites, video, messaging. And we pushed it onto phones, Wi-Fi, and cloud infrastructure. But the zoomed-out view matters. The latest ITU estimates still put about 2.2 billion people offline. So ubiquitous is aspirational. The tracks still don't reach everyone.
And for the people who are online, the plumbing is getting rebuilt while it's running. Encryption is becoming the default expectation, and services like Let's Encrypt have helped push HTTPS to hundreds of millions of sites. At the same time, the industry is beginning a long migration toward post-quantum cryptography. New standardized algorithms designed to hold up even if large quantum computers arrive.
So, here's the recap. Packets made it resilient. TCP/IP made it interoperable. The web made it usable. And now encryption and the rules around identity and trust are shaping how safe it feels. Next time a page won't load, ask yourself, is it the train or the tracks? Thanks for joining us for this timeline of the internet. And if you want to see what happens when the tracks run under an ocean, the vintage cable chart on screen is your teaser. Subscribe for our next episode on submarine cables. See you then.